way back to grade 9. Simplifying polynomials. How did you do it? Combine like terms. And what's the definition of a like term? Yes?
It's like something or like a number with the same variable. No, I
No, you're right. Same variable and same.
And same exponent.
Exponent. Coefficients can be different. So you might have seen the circle technique. Maybe you didn't. Doesn't matter if you did or not. But we tend to circle the like terms. So if I have 3x and then I take away 2x, how many x's do I have? Okay, so just x. And then I have 5y and 4y. And how many y's do I have? Doesn't this seem so easy when you go back now? We're going to do the exact same thing with radicals. So you'll notice I kept all the coefficients exactly the same. It's still 3, 5, negative 2, and 4. I'm going to do the same circling technique. I'm going to add the radical x's. So if I have 3 radical x's and I take 2 of them away, how many radical x's do I have? Just 1, root of x. And you notice we call it radical, we call it root, we call it square root, all means the exact same thing. Then here I've got 5 radical y, and I've got another 4 radical y. How many radical y's do I have? So I have 9 square root of y. It works exactly the same with radicals that it does with x's and y's and polynomials. Okay, let's mix it up a little bit. Now the coefficients are going to be the same, and here instead of variables, I'm putting numbers underneath. So what I'm going to look at first is the like terms of root 3's. So I have 3 root 3, and I have negative 2 root 3. How many root 3's do I have? 1 root 3. And here I have 5 root 2's and 4 root 2's. How many root 2's do I have? Plus 9 root 2. Do you see the pattern of what's happening there? And we just want to make a note, and I'm grabbing my red pen because notes are usually pretty important, so I like to write them in red. The value of the radicand does not change. The value of the radicand does not change. So here I had root 3, and I combined it with a root 3, and what did I end up with? Root 3. I didn't combine those to be root of 9. I didn't combine them to be root of 6. I just left it as root 3. Same thing here. I had root 2, and I combined it with a root 2, and I ended up with a root 2. I'm not changing the radical. All I'm doing is changing those coefficients.
If you were to get root of 9, that would be multiplying, yes?
Correct, and that's what we're doing tomorrow.
Okay, yeah, that just kind of sparked in my head.
Questions so far? Okay, grab your paper because now we're going to go to paper for the examples. Here's the method for adding and subtracting all questions with radicals. Step number 1. Simplify all radicals. That's what you did on Friday, and that's why you did it, because it's the first step of adding and subtracting. Step number 2, combine like radicals. So exactly the same way as like terms, we do with like radicals. That's it. Simplify, combine. So we're going to start really simple, and then we'll work up to the harder ones. So example number 1, little root 3 plus a 4 root 3. So the first thing we do is we just look at the radicand and see can we simplify. So that's what you did on Friday. Are there any factors in 3 that are a perfect square? No. So we can't simplify those. They are what they are. 3 is as low as we can go. Now we just combine them. If I have 1 of something and I have 4 more of something, how many somethings do I have? 5. So if I have 1 root 3 plus 4 root 3, what do I have? 5 root 3. You'll notice that radicand did not change. All I did was just add up how many I had. Example number 2 with a cube root. And this is how we're bringing it up from last semester, because you probably didn't do cube roots in grade 11, or grade 10 is my guess. First little thing we do is we check, can I simplify 7 or can I simplify 5? Are there any perfect squares hidden in the factors of 7 or 5? Okay, now I combine like terms. I have 1 cube root of 7 and I have negative 1 cube root of 5. Can I combine these? So this would be the equivalent if I gave you x minus y and I said simplify. What would you put down if I said simplify x minus y? X minus y. So this cannot be simplified, it's just itself. And so the purpose of the example was just to show you what to do when they are not like radicals. It's already simplified. Do you see the link to polynomials? Example 3, we're just going to put a bunch of stuff in here. So a root 3 minus a 5 root 2 plus a 6 root 2 minus a 7 root 3. If you like the circle technique for polynomials, do that. There's nothing wrong with that. If you're not visual and that doesn't help you, then don't do it. I'm going to circle the root 3's first. And now we're just going to add. If I have 1 root 3 minus 7 root 3, how many root 3's do I have? Minus 6 root 3. Then I'm going to box the root 2, so I have minus 5 root 2 and plus 6 root 2. How many root 2's do I have? And you know I don't need to write the 1, we just write it as root 2. So if you like this technique, do it. If it does nothing for you, don't do it. It's completely up to you. Okay, let's step it up. Cube root of 54 plus cube root of 16. Here's why we need that step number 1 of simplifying. If we just look at these as they are these like radicals? Are these the same? No, 54 different from a 16. Well, let's look what's going to happen once we simplify. So we'll start with the 54, and you can do the factor tree. You can list out the factors. It's completely up to you how you get the prime factors. That's up to you, the method that you like. Factors of 54. 27 and 2, good place to start. Is either of those prime? 2, so I'm going to keep the 2. What do I do with 27? Kind of. Break it down into 2 multiples. 3 times 9, and then I still have that times 2. Which one of those can I break down? So then 3 times 3 times 3 times 2. There's how to do it sideways if you like that better than the vertical tree. If you like the vertical tree, then do the vertical tree. I'm just giving you different ways. And so we can simplify this up into 3 to the 3 times 2. And so what was the purpose of that? Why did we do that? Why did we suddenly make it more complicated to make it more simple?
So that way we would be able to separate what's what, and we'd have a cube root, and then we would know what our coefficient is.
Perfect. And what happens when you cube root and then put an exponent of 3 on something? They cancel. So our coefficient is going to be 3. And what's going to be left? Cube root of 2. That should be from Friday. That should make sense in your head. Yes, no. Okay, let's do the same thing with 16. And I like to break it up in groups of 3. I don't know if Mr. Roseman taught you this or not, but I like to write it as 2 to the 3 times 2, because then I can see that 2 is going to come up front. If you don't like that, don't do it. It's completely up to you. And so the reason I write that 3 separately is just to be able to see visually here what's going to happen with a cube root and an exponent of 3. It's going to cancel. And what am I left with? Cube root of 2. So if we hadn't simplified these, we would have said, oh, well, this is already simplified. But take a look now. Once we simplify them, what do you see? Right, a cube root 2 and a cube root 2. So now we can add them together. If I have 3 on the left and 2 on the right, how many do we have? 5 cube root of 2. There is a little 3 there, but you can't see it. So that's why we need that step 1. It's why we learn to simplify, because we have to do that as a first step to make sure they're not the same. Questions so far? It's not equal to anything, so it doesn't say equals 0. This is just an expression, so you can't solve an expression. So we just leave it like this, done. But what is the cube root of 2? We don't like decimals. We like the roots better. Yeah, if we had our calculator, sure, we could get a decimal value, but what's the purpose of that, right? But why, right? Because this, to me, as a mathematician, this is a number, right? I'm happy with this. So the only reason we would use our calculators is if we were trying to do something with it, find a volume, find an area, but we're not. We're just going to leave it. Black pen. Number 5, let's put some variables and some coefficients in there. Biggest mistake with questions that are really complicated like this are things like this too, is we need to know, is that an exponent on the b, or is that the index of the radical that's following it? How do we know that's an exponent on the b and not the index of the radical? It's not on top of that little line, plus would we ever write a 2 if it was the index? No, so this is an exponent.
Oh man, you remember last year in my class when that so taught me?
No, I don't remember that.
Trust me, I do. I remember I was so confused about it.
Does anyone know why the radical sign looks the way it looks? So what's the history of that? Where does it come from? Yeah, it's actually not. It's actually pretty cool when you think about it. It comes from the letter R. And what does R stand for? Radical. So initially they used to do an R with a 3 underneath it, and then when they were converted to a typewriter, they couldn't actually get it underneath the R, so they invented a new symbol. So it's just an R for radical, which is kind of cool. Okie dokie, 75. I'll do vertical this time. I like to circle the primes so that I can see when that branch ends. Completely up to you how you do the question. You do not need to show me the tree. You don't even need to show me stuff like this. As long as you show me this, I'm fine with that. So if your brain can automatically go to 5 squared times 3, great. You don't need to show the work. If you want to show the tree, show it. There's nothing wrong with that. So I'm going to split this 75 into a 5 squared and a 3. What am I going to do with that b to the 5? Yep, so a b squared and a b squared and a b. If you wanted to combine the b squared and b squared to be b to the 4th, that's great. You don't have to, but you can if you want to. It's up to you how you choose to write it. Still got this negative b squared hanging around. Now I got to do something with 32. 32. Reese is like the master prime factor today. If you want to break this up into groups of 2, how can we break it up? Again, you can leave it as b to the 5 and deal with it that way, or you can break it up. It's completely up to you. So a 2 squared, and a 2 squared, and a 2, and then I still have that b hanging around back there. What I do then, because I'm visual, is I circle everything with a 2, because what it tells me is that's going to go outside, and anything that's not circled is going to stay inside. So if you're visual, that trick sometimes works. If you're not visual, don't worry about it. So it means that a 5 is going to come outside. A b and a b are going to come outside, which is going to give me b squared. And where you could have got that from before, if you left it as b to the 4, then you divide by 2 to go outside. And then what's going to be left inside? 3. Oh, I heard b cubed. B, because b is the one that's not circled. Okay, so the circling tricks help some brains. This guy, a 2 is going to come outside, and a 2 is going to come outside, which is going to give me, which is?
4.
Then I got the b squared that's already in front. What's going to be left in that radical? Or not to be? A little math joke there for you.
Math/Shakespeare.
A little bit. Question so far just on the simplifying, because that's all from yesterday. We haven't actually done the new stuff yet. Just want to make sure that makes sense. Okay, step number 2, combine them. Can't combine them, so what do?
Leave it like that.
We just leave it. That is simplified, which I understand this looks a lot less simplified than the one up here. You just need to trust me. We'll come to it later on. This is actually very simple to a mathematician. I know. How are you feeling so far? Number 6 is about as hard as they're going to get. We have a 3b. Now, is that a b cubed or is that a cube root? How do you know it's a cube root? And then I got a 2 cubed or cube root? Another cube root. Okay, step 1 is to simplify. Another trick for visual people is sometimes this is a lot in one question, so if you just cover half, sometimes it's just less visually overwhelming, and just simplify that, then cover the other half, simplify that, because some brains, when they see it all, it's a lot going on. So just a little trick. Okay, 40, what do you want to do with him? What would you like to break 40 into? And so when we combine it, 2 to the 3 times 5. So again, if you don't want to show all these steps, that's fine. If you just gave me the 40 and the 2 cubed 5, I'm fine with that. However you get there, whether it's horizontally, whether it's factor tree, completely up to you. So what do I do with this 3b that's kind of outside here? I just leave him. Not going to worry about him right now. I'll worry about him in a second. Now all I'm going to do is split that 40 up into 2 cubed times 5, and then still that b hanging around in the back there. Again, little trick I use is I circle anything with a cubed, because I know then that's going to come out front. Why in the last example did I circle things with a 2, and now I'm circling something with a 3? Awesome. So what happens to this 2 cubed? He's going to come outside, and when he combines with a 3b, what's going to happen? Almost, except it's all multiplying. He's going to end up being 6b. So it's 2 times 3b is where I'm getting that from. And what's going to be left under there? Well, anything that's not circled. That's why I like to circle, because it's a little visual what's left. There's going to be a 5 and a b. Oh, yeah, it's just my little tail isn't there. Better? Awesome, thanks for asking. 135. 5 times something, something. 26, 27. And then 9 will be 3 times 3, so in total we're going to have 3 to the 3. What do I do with this negative 2 up front? Yeah. What do I do with the negative? I just stick him in front. I just leave him where he is for now. And I'm going to write the cube part first, because my brain likes it to be in front. So my negative 135 is now negative 3 cubed times 5. What do I do with this b to the 4? So I want to put him into groups of 3, so a b 3 times a b. Again, I like to circle just because visually it reminds me what's coming out front. If you don't like that, don't feel you have to do it. Be careful here with the negative. When I bring this negative 3 out front, I've got to multiply it by a negative 2. What's going to happen when I multiply a negative 3 by a negative 2? It's going to become positive 6. And then when I bring this b cubed out front, he's going to be just b. What's left? What did I not pull out front? I like that word compatible. I like that. Can we combine these? How do we know? Oh, I forgot the cube. Thank you. How do we know we can combine these? And they have to have the same, what's the vocabulary word? Radicand and index. Same radicand, same index. Ellie, you just have to take your earphone out for me, please. So if I have 6b here and I got 6b here, how many b's is that? So I have 12b times the cube root of 5b. Notice that did not become b squared. Why did that not become b squared? Perfect, because we're adding. So 6b plus 6b is 12b when we smush it together. That's as hard as they're going to get. It's a double simplifying and common bases at the bottom. How are we doing? I was trying to ignore it for the moment. Word problem, grab your highlighters. And the script is more important than math.
No, it just happened to be a good coincidence.
I didn't say more fun. Just read to read. Don't overthink it. Read to read. Sentence in a book. Don't overthink it. Don't do the math. Just read. This is what your brain probably did. Perimeter, square, side length, blah, blah, blah. That's why we read twice, because that's what the brain's natural tendency is to pick out the words first. So we probably need perimeter. It's a mathy word. We probably need square. It's a mathy word. Side length, this whole mess here, and simplest form. I left out find the of with of the in. Okay, what do you want to do? Okay, why? Okay, so we're going from perimeter to side length. It's a P, perimeter to side length, just my notation. So when we're going from perimeter to side length, do we want to multiply? No, we want to end up dividing, always when you go from perimeter to side length. Oh, we're finding the perimeter. We have the side length, and we're going to the perimeter, which means we want to multiply. High five. How do we know we want to multiply by 4? So what if I changed this question and made it a triangle? What if I made it a pentagon? What if I made it a nonagon? Nice. So we're going to do 4 times this guy, cube root of 27, w to the 4th, g to the 8. Now what? Okay, how do we simplify this mess? Okay, so what do I do with this 4 that's in front? I just leave it.
Let it be a 4.
Yep, he can just hang out in front by himself. What do you know about 27? What do you want to do with w to the 4? Except it's a cube root, so squared and squared probably isn't the best choice. And then g to the 8. I heard a g cube and a g cube and a g2. It sounds like GQ, the magazine. So what's going to come out of front? Well, this cubed, this cubed, this cubed, this cubed. They've got to come out front. Again, if you like the circling, use it. If you don't have to. What happens to a 3 cubed when we take it out front? Right, so it would become 3, and because there's a 4 already out there, what do we do with it? Multiply it. What happens to this w cubed when he comes out front? We're going to have a g and a g when we cube root it, and a g times g is going to make? And then what's left? What's not there? Final answer. Nope. Usually, well, these no. This, the 12 would have to come in front. But in here? Don't care. Questions? I want you to find your